Okay. So hello and welcome to week six of the category theory course. Uh, I'm Shubhajit Das. I am a PhD student at the Department of Mathematics in ISC, and as we keep doing every week, we'll be solving problems based on the content of this particular week. Okay, so we'll start, but first we'll give a small recap of what has been covered this week. So this week was, I mean, probably one of. So this is like the sixth week. This is like we are almost midway in the course, and so this week talked about the very important notion of adjoint functor theorems, and perhaps the general adjoint functor theorem, which sort of gives you necessary and sufficient conditions under which a given functor has a left adjoint. So maybe yeah. So in this week we saw the notion of the unit and the co-unit associated to an adjunction. So what is the idea? So given an adjunction of functors, F is the left adjoint, G is the right adjoint, then you can define two natural transformations. One of them is eta, which is from the identity functor on script A into GF. This natural transformation is called the unit of the adjunction, and this is exactly given in this way. So what is the component of eta at an object A? It's supposed to be an arrow from A to GFA, and this exactly corresponds to the identity arrow from FA to FA under the natural isomorphism given by the adjunction. So eta is your unit. Eta is called the unit of your adjunction. The unit natural transformation associated to the adjunction. Similarly, or rather dually, you also obtain something called the co-unit of an adjunction, which is a natural transformation from Fg into 1b. This is called the co-unit natural transformation of the adjunction. And maybe I should put a the. Okay. And how is it defined? So epsilon at an object B is supposed to be a map from FGB into B, and this exactly corresponds to the identity arrow from GB to GB under the isomorphism given by that adjunction. Right. The interesting thing is, given any adjunction, so that you can consider the unit of the adjunction and the co-unit of the adjunction, you see that the unit natural transformation and the co-unit natural transformation satisfy what are called the triangle identities. So what are they exactly? So one of them says that if you start with your functor f, go to FGF via the natural transformation f eta. So eta is from one script A to GF. So f eta will be from f to FGF. And from FGF, if you go to f, which is via the natural transformation epsilon f. So epsilon is from FG to one script B. So epsilon f is from FGF to F. Then this composition is supposed to be the identity on F. This triangle commutes. So this is, this is a commutative diagram in the functor category from A to B, right? So this is the first triangle identity. The other one is the dual one. So you start with G, get to GFG using eta G, and from GFG to G you have G epsilon. Again, this composition has to be 1G, the identity natural transformation of the functor G. And this is a commutative diagram in the functor category from B to A. So the interesting thing is, whenever you have an adjunction, there is you have the co-unit of the adjunction, you have the unit of the adjunction, and they satisfy the triangle identities. But the interesting thing is, if you have a pair of natural transformations eta and epsilon with directions as indicated, so the natural transformation eta is from 1A to GF and epsilon is from FG to 1B, then you get an adjunction between the two functors F and G with F on the left and G on the right. And in fact, the unit and the co-unit of this adjunction are eta and epsilon respectively. So conversely, every pair of natural transformations eta from 1A into GF I'm sorry, yeah, every pair of natural transformations, every pair eta is from 1A to GF and epsilon is from FG to 1B of natural transformations gives an adjunction. And I'll okay, yeah, so it, every pair, conversely every pair of natural transformations gives an adjunction, and as I mentioned, this process is entirely a bijective process, and in fact there is a 1-1 correspondence, a bijective correspondence, a bijection. So A, B, F, G, an adjunction between two functors F and G with F being on the left and G on the right, and pairs eta from 1A into GF. Oops. So eta is a natural transformation from 1 on A into GF, and epsilon is a natural transformation from FG into 1 on B. So you have a bijection between the two. So in fact, recall how we usually define an adjunction. So we use Hom sets, and we use a natural bijection of Hom sets to define an adjunction. Now, since there is a bijection between these two, that is adjunctions between F and G with F being the left adjoint and G being the right adjoint, and pairs of natural transformations eta and epsilon, where eta is from 1A into GF and epsilon is from FG into 1B, satisfying the triangle identities. Yeah. The interesting thing is, even though, so the point is, the notion of an adjunction is not just something you can, you will just restrict to categories themselves. It's something called a two categorical notion. Okay, in the sense, we won't get into the details of what two categories are, but the idea is, in a category you have objects and you have arrows to compare objects, right? Now, you might ask this question, what happens if I want to compare two arrows? So for example, if there are two arrows from an object to another object, you might also ask for a notion of comparing, or a notion of an arrow from the upper arrow to a lower arrow. So this is like a two-dimensional arrow which has as its domain and codomain one-dimensional arrows. Right. So this is something called a two categorical notion, and you have already seen an example of a two category. For instance, cat itself is a two category. The objects are categories. The one dimensional arrows are functors of categories, and the two dimensional arrows are natural transformations. Okay. So this is an example of a two category. Now, the notion of an adjunction can act, I mean, if you focus on this definition, you see this definition is entirely made up of two natural transformations and two triangle identities, which are precisely just equations. So what this essentially means is you can make, or rather use this definition or try to imitate this definition inside a two category actually. So that is why you can actually define something called an adjunction internal to a two category. So I'll just make a small comment. So general, or maybe internalizable in two categories, two dimensional categories, in which there is a notion of a map from one map to another map. So this is the utility, I mean, this is the idea of mathematics, and in category theory in particular, you try to reformulate something in a slightly different way, and it turns out that this new definition can be has more applicability in, I mean, can be used in different contexts. So this is one of those instances. Anyways, so adjunctions can be characterized using pairs of natural transformations eta and epsilon satisfying the triangle identities. This was one of the things that you learned this week. Moreover, even more interesting, you also learned about the general adjoint functor theorem. So, which as I mentioned gives you necessary and sufficient conditions. For a functor to have a left adjoint, let's say, it turns out that this theorem is really powerful. I mean, of course, you know that if a functor has a left adjoint, that is, if the functor is itself a right adjoint, it will preserve limits. But having existence of an adjoint is something really powerful, and this is precisely given by the adjoint functor theorem. So the idea is pretty simple. Firstly, you talk about some idea of, I mean, the entire theorem is based on something called the solution set condition, which talks about a condition under which a particular category has an initial object, and the theorem is then the adjoint functor theorem sort of entirely revolves around this condition. So if this solution set condition is satisfied, then your functor will have a left adjoint, let's say. Okay, so we won't mention the theorem once again, we won't be doing that, but yeah, it's a really powerful theorem, but entirely based on simple ideas. So the idea is you first have some condition for existence of initial objects, and then try to use that to describe an existence of some adjoint functor, left adjoint functor. And note that initial objects themselves can be defined in terms of left adjoints. So it sort of is like a full circle. Okay, so let's start the problems. Yeah. Okay. So you start with an adjunction UF, where U is a functor from A to set and F is a functor from set to A. And suppose that there exists an object A in A, such that if you look at its image under the functor u, so that is a set. This set has cardinality at least 2. What you are being asked here is to show that this functor f, I mean the left adjoint f, is a faithful functor. So how do you show this? This is a really good problem. You have to show that the left adjoint is faithful. Any ideas, Shrutin? You can hear me, right?
Yeah, I can hear you. I'm not sure.
Okay, okay. Think about it for some time. Okay, I'll give you a hint to start with. So, uh, so in this particular week, you also learned something. I mean, to characterize faithfulness and in fact fully faithfulness of adjoint functors using the unit or the co-unit of an adjunction, right? That was covered this week. So, for instance, you learned that if you have an adjunction of categories, let's say f is the left adjoint, g is the right adjoint, then the left adjoint f is fully faithful if and only if the unit of of the adjunction is a natural isomorphism, right? And dually you have a theorem for the right adjoint. So I mean, even if you don't remember that, I would ask you to think about it. What would happen? Or let's say I am also mentioning that f being the left adjoint being faithful implies something for the unit of the adjunction. So what can we say? So uh, just tell me if you have seen this week. So claim is f is faithful if and only if the unit of the adjunction is a monomorphism. Have you seen this week?
Yes, sir.
Okay, you have. Okay. So what does it mean to say that eta is a monomorphism? So we'll always denote the unit of an adjunction by eta. So eta from 1a, identity functor on A into GF is the unit of your adjunction. This natural transformation is a mono in your functor category from A to A if and only if each component arrow of eta, so the component arrow of eta at the object A, which is an arrow from A to GFA, is a mono in A. I was going to put an exercise on this as well, but maybe that will be covered later in the week, later in the course, or maybe it has already been covered. That so you know that natural transformations are isomorphisms if and only each of their components are isomorphisms. But this idea is also all this result in fact holds for monomorphisms and epimorphisms as well. So a natural transformation is a monomorphism in a functor category if and only each component of it is a monomorphism, and dually a natural transformation is an epimorphism in a functor category if and only each component of it is an epimorphism. Uh, have you seen this this week or this sometime before? if you haven't, try to think of something, some idea. The proof is pretty simple. The idea is based on this, that monomorphisms in a category have a limit characterization. You can characterize them in terms of pullbacks. If you, so a morphism will be a monomorphism if and only if its pullback along itself consists of identity arrows. That is in other words, its kernel pair consists of identity arrows. So monomorphisms can be characterized in terms of pullbacks, and you know that in functor categories, limits and colimits are computed object wise. So that is a precise idea. Pretty simple but pretty powerful as well. So yeah, to show that our left adjoint functor is faithful, it is enough to show that the unit natural transformation of the adjunction is actually a monomorphism. That is, in other words, we need to show that each component eta A, which is an arrow from A to GFA, is a monomorphism in A. Sorry, I think I messed it up a bit. So here, A, instead of A, you should have set, right? One set. There's no G here. There's U here. So F is a functor from set to A. U is from A to set. So UF is from set to set. So in set comma set, I should say. And let's say eta at S from S to UFS is a mono in set. In other words, that is eta at S from S to UFS is, and we know what monomorphisms in sets are. They are precisely injective set maps. So is an injection, right? That is what we need to show. So we need to claim that eta S is actually an injection. So how do you show this? So so let's quickly understand what we are doing. So to show that our left adjoint functor F from set to A is faithful, it is enough to show that each eta S is an injection for each S in set is a mono in set for each S in set. Right? So this is what we need to show, that eta S is an injection for each S in set. So how do you show this? So I'll give you 2 minutes to think about this. So the idea is pretty simple. So we need to show that each component of eta is an injection, right? How about we focus on some particular components first? I mean components at some specific objects first. So observe that by the triangle identity, F to FGF, sorry, not this one, this won't work. The other one, G to GFG, this is eta G, GFG to G, this is G epsilon, and this is identity, natural transformation from G to G. So observe that by this triangle identity, what you have is, that is, the identity basically says that G epsilon composed with eta G is 1G. So what this means is that as a natural transformation, eta G has a left inverse, right? Which means that eta G is a section, that is eta G is a split monomorphism. So in particular, eta G is a monomorphism. So let me add a page quickly. We have eta G is, okay, so let's write the direction of eta G. Eta G is from G into GFG, the unit of that. I mean, yeah, eta G natural transformation, where eta is the unit of that junction, uh, is a split monomorphism. In the functor category B2A, which implies, okay, I keep using G every time. Let's replace G by U. So U to UFU. So this is eta U, and this is U epsilon. So U epsilon composed with eta U is 1U. So we have this, that eta U from U to UFU is a split monomorphism in the functor category. Yeah. So the direction of U is A to set. Right, we have this, right, which means that eta U at an object A at some okay, so we already have a we have already fixed an A. Let's say this is okay, no, eta U at an object, I don't know, let's say C. From UC into UFUC is a monomorphism in set for each C in A, which implies that what is the component of the natural transformation eta U at, say, this is exactly eta at UC. So yeah, I do not need to write this again. Eta U at C is just eta at UC. So eta at UC is a monomorphism in set. So in particular, this means that eta at UA, where A is our object, we have assumed that there is some object A in your category such that the A is some object in your category such that the cardinality of the set UA is greater than or equal to 2. So we have eta at UA is a monomorphism in set, right? So what does this mean? Eta at UA is a monomorphism. Let's write the domain and the codomain. So eta at UA is a map of sets from UA into UFUA. Now what was our assumption on the set UA? So UA is a set which has at least 2 elements, right? And eta at UA is a monomorphism, which implies that so if you take 2 elements, let's say x1 and x2 are in UA, distinct elements which exist exist by assumption, what you have is eta at UA applied on x1 is not equal to eta at UA applied on x2, because eta at UA is a monomorphism in set, that is an injective map, right? So an injection. Right. And now what we just need, so we have something about eta at UA. What we just need to do is we need to show that for every set S, eta at S from S to UFS is an injection, and as is apparent, so we have something, I mean, look at what we have. So we have something about eta, I mean some component of eta. We want to deduce something about all components of eta, right? What is the best thing that you can do, or what is the thing that you can use here to relate one component to another component? That is exactly the naturality of the natural transformation. That's all, right? So what we would want is to obtain a naturality square which connects eta at S and eta at UA, right? So let S be any set. Okay, and so we want a naturality square, so we should first start with a map, right? So let S be any set, and we consider the map. Consider a set map, let's say. Consider a set map from S to UA, right? Okay, okay, we want, okay, let's go step by step, let's not jump. We want, this is what we wanted, eta at S from S to UFS is an injection. This is what we want, right? So let how should I say, let S1 and S2 be distinct elements of your set S. Assume that eta at S of S1 is equal to eta at S of S2. Okay, we want to reach a contradiction because we want to show that eta at S is an injection. So consider a map, consider a set map, any set map from S to UA. What does this map do? So let's call this map, I hope I haven't used F anywhere so far. So consider a set map F which sends S1 to which sends S1 to, so we already had something, right? Yeah, x1 and x2 are two distinct elements in UA. So S1 to x1 and S2 to x2, let's say. Okay. We can do this because x1 and x2 are distinct elements and S1 and S2 are also assumed to be distinct. I'm not sure exactly if this would work, but let's see. Yeah, let's see. So this generates a naturality square. This generates a naturality square. Yeah, by the way, the map F on other elements of S is defined as you want. Okay, so you can maybe send all elements except S2 to x1. Okay. So this generates a naturality square. So that is why maybe I should write take some set map. Take one set map which does this. So S to UFS, you have eta at S, and what else? UA to UFUA, eta at UA. S to UA, you have your F, and UFS to UFA, you have UF applied on F, right? This commutes. Okay, so let's see if this works at all. So we can take S1 and S2, eta at S applied on an S1, they are equal under UFF. They are, yeah, I think this should work. Okay, so UF of the naturality square. Okay, so let's not write much. You start with S1 under eta s it gets mapped to eta s of s1. Under uff it gets mapped to something, some element uf f applied on eta s s1, right? If you go on in the other direction, so I mean follow the other path, so you have f s1 which is x1 by your assumption, and eta at ua applied on this is eta at ua applied on x1. This should give you a contradiction. Right, so eta at ua applied on x1 is this, right? Similarly, if you start with s2 on the other hand, let's use a different color for this. I don't know if this will work. S2, yeah. If you start with S2 on the other hand, you arrive at eta S at S2. Now keep in mind or recall that eta S at S1 was assumed to be equal to eta S as at S2. So these two are equal. Under UFF, this gets mapped to UFF of eta S at S2. These two are equal as well, right? S2 under F gets mapped to F of S2, which is exactly X2, and eta at UA takes this to eta at UA applied on X2, right? But eta at UA applied on X1 was different from eta at UA, different, they were unequal, right? And that is what you have. I mean, that is a contradiction. So to be precise, or let's write it nicely, precisely, you have from the commutativity of this square, UF of F composed with eta at S is eta at UA composed with F, which implies that UF of F, so if you apply it on S1, let's say, so which implies that UF of F applied on eta S at S1 is equal to UF, okay, so let's write it like this. I'm sorry, we should rather write eta at UA applied on F applied on S1, right? This is just X1. So eta at UA applied on X1 is equal to eta at UA applied on FS1, which by the commutativity of the square is eta at UFF applied on eta S at S1. Since we know that eta S at S1 was assumed to be eta S at S2, so this is exactly equal to UF of F of eta S at S2. This is equal to, again by the commutativity of the square, you have eta at UA of F of S2, which is eta at UA of X2. This is a contradiction. As eta at UA is, let's write it properly, from UA into UF UA. Oh, yeah, as eta at UA from UA into UF UA was injective and x1 is not equal to x2. Right? Those were two distinct elements we chose. Right? So this is our contradiction, and the contradiction entirely arises because we assumed eta at S applied on S1 is equal to eta at S applied on S2. So eta at S applied on S1 is actually not equal to eta at S applied on S2, which implies, since S1 and S2 are arbitrary elements in capital S, so eta at S is an injection and this is for each set S in set, which implies that eta, the unit of the natural transformation from one set into UF, is a monomorphism, which implies that our functor f from set into A, the left adjoint functor, is faithful. And that's it, we are done. Okay. Yeah, so it's pretty simple. I mean, the solution doesn't look like it, but it is. So the crucial idea is to use the triangle identity, and this is actually true in general. Whenever you have an adjunction between two functors f and g, with f the left adjoint and g the right adjoint, if you look at so if eta is the unit of that junction, epsilon is the co-unit of that junction, you have this triangle identity with u being replaced by g, then eta g is always a split monomorphism. Eta g always has a left inverse. So eta g is in particular always a monomorphism in the functor category from B to A, where G was from B to A. Okay, that is the idea that we sort of exploited for this. Okay, let's come to our next problem. Okay, so this would be a bit long, I would assume. That is why I would only highlight the important steps in the problem. So it's a pretty, I mean, this is something that you would assume, would expect to happen. So the idea is, suppose C is a category. This is our notation that we define. So for a functor f from A to B, we consider another functor f upper star, which is precomposition with f. So it's a functor with domain the functor category from B to C, and codomain the functor category from A to C. What it does is it sends any functor h from B to C onto the functor h composed with f, which is now a functor from A to C, and sends a natural transformation alpha onto the natural transformation alpha f, the Godunov product of alpha and the identity natural transformation on f. So what you are being asked to show is that with this notation in mind, suppose that you have an adjunction between functors f and g, with f being the left adjoint and g being the right adjoint, and suppose you take some category C. What you want, so you can consider the induced functors f upper star as indicated in this direction and g upper star as indicated. You have an induced adjunction between these two functors, but now g upper star turns out to be the left adjoint and f upper star turns out to be the right adjoint. So this is something that is what should I say, pretty something which one can expect, something which is a bit natural actually. We'll get to why I am calling it a bit natural or something one can expect. But before that, let's give a rough solution. You can check the details fully. So the idea would be to use, so we want to use the unit co-unit characterization of adjunctions. So what we want is, so consider a natural transformation eta hat, let's say, from 1 A comma C into f upper star g upper star. This will be our unit, right? F upper star is the right adjoint, g upper star is the left adjoint. So the unit of our adjunction should be in this direction, from from the identity functor on the domain of the left adjoint to f star g upper star. Okay, and how do we actually define this? So eta hat, the component of this natural transformation at h, should be a map from the functor H. So should be a natural transformation from H into F upper star G upper star applied on H, which is just H composed with G composed with F. And we know that the unit eta of our original adjunction is a natural transformation from 1 to GF, and that is what we are using here. So we declared this natural transformation to be H eta. So since eta is from 1 to GF, H eta is from H to HGF, right? So check naturality for this one. At the same time, or rather also, in fact, you need to check naturality in for two different things, right? Firstly, you need to check naturality for this one, the fact that this is a natural transformation, which is obvious because eta is a natural transformation and H eta is just 1H star eta, the horizontal composition of two natural transformations. So, we have used this notation many times, but I'll still write it once more. The Godemov product of these two natural transformations. So this is a natural transformation. You have seen this. You also need to check naturality of this. That is, eta hat at H is natural in the variable H, or rather eta hat defined from this functor to this functor is a natural transformation of functors. So check naturality, and maybe I'll mention, to be very explicit, check naturality in the variable H in the functor category A to C. Okay. Again, we define, so the claim is that this will be the unit of your adjunction. We also want the co-unit of our adjunction. So define epsilon hat, which should be from 1 on BC into sorry, not one, yeah, it's supposed to be the co-unit, so it should be from FG, which in this case is G star F star. G star is the left adjoint, F star is the right adjoint, into 1 on the functor category from B to C, right? And what is this? So its component epsilon hat at some object H. We have used H, let's say K, which is a functor from B to C, should be from G star F star applied on K, which is just exactly K composed F composed with G, to K, right? And we know that if epsilon denotes the co-unit of the original adjunction, then epsilon is from Fg into 1b. So we can just take this to be K epsilon, right? Epsilon is from, as I mentioned, K. So K epsilon is from K composed F composed G into K. Yeah. I hope I didn't mess up with the notations here. So F is from A to B, G is from B to A, H is from A to C, right? Yeah. And G is from B to A, F is from A to B, and K is from B to C, right? Yeah. So yeah. So also check naturality for this one. In the variable K in the functor category from B to C. So what do I essentially mean by naturality? That this should be a natural transformation, which means that if you take any arbitrary arrow in the functor category from B to C, so if you take any arbitrary natural transformation from, let's say, some functor K to some functor K prime, you should have a square, and that square should be commutative, right? So finally, using the triangle identities or the zigzag identities, as I like to call them, triangle identities for eta epsilon, right? Verify the triangle identities, and perhaps you also need to use naturality at some point of maybe eta or maybe epsilon or maybe both. Verify the triangle identities for eta hat and epsilon hat. Then it turns out that eta hat, which is from 1 on the functor category from A to C to F star G star, is the unit of some adjunction, and epsilon hat is the co-unit of some adjunction, and I mean G upper star will be the left adjoint of this adjunction, F upper star will be the right adjoint of this adjunction. We are using exactly the characterization theorem for adjunctions. So this gives you an adjunction. Checking the, I mean verifying the triangle identities for the unit natural transformation eta hat and the co-unit natural transformation epsilon hat. I mean, we shouldn't call them unit and co-unit a priori because we haven't really obtained an adjunction. So checking them for these two natural transformations should give you an adjunction between, or maybe adjunction with F the left with G upper star the left adjoint and F upper star the right adjoint. And in fact the unit, and now you can say that the unit natural transformation of this adjunction is eta hat and the co-unit natural transformation of this adjunction is epsilon hat. Okay, so I'll just mention one thing here. Yeah, for H in A comma C, the component of the natural transformation. So for all objects H in A comma C, we define eta hat at H in this way, and for all objects K in B comma C, we define epsilon hat at K in this way. Okay. Okay, so that essentially solves the problem, but I'll give you an alternate perspective on this. Maybe we cannot get into the full details, but why exactly was I saying that this is something that you should expect is the following. So maybe I'll use a different color for this. So an alternate proof or sketch, maybe of sketch of proof, which is a two categorical perspective. So observe that for any category C, if you look at this functor bar comma C, so I mean what this does is that this is a functor from cat op into cat. Okay, where when I say cat op, I mean I'm actually referring to the two categories, functors and natural transformations, with the functors being reversed in the reverse direction, that is. Okay, so yeah, okay, wait for some time, we'll wait for some time. I think I need to charge my pencil. But yeah, as I was saying, that cat here actually denotes the two categories, functors and natural transformations. And what this does is, this bar comma C is, it's actually something called a two-dimensional functor. Okay, so it's a it's a map from cat op to cat that takes objects to objects, that is categories to categories. Of course, we know that if A is a category, then the functor category from A to C is itself a category. Then this is also, by the way, sometimes called an internal hom of cat, because it's behaving like a hom functor, but instead of going to set, you are staying inside cat even after applying this. It takes a functor to some functor, and it takes a natural transformation to some natural transformation. And the idea is precisely this, that if you start with an adjunction in cat op, since this is a two functor, it's supposed to carry that adjunction to an adjunction, and that is exactly what is happening. So this is exactly what I wanted to highlight. Okay. So what this does is, so think of, as I mentioned, this is a cat is a two category of categories, functors, and natural transformations. Cat op is again the two category of categories, functors, and natural transformations, but with the direction of the one cells reversed. I mean the one dimensional arrows that I was talking about today. Okay, so what this does, it takes a category A, maps it to A comma C, takes, let's say, a category B and maps it to B comma C, takes a functor F from A to B. So I should say F op. So F is a functor from B to A. If you just look at the formal arrow which is in the opposite direction from A to B, that is what I was talking about when I was saying that reversing one cells. So if you look at, I mean, you understand what the category cat op is, right? Forget the natural transformations. The objects are the same, and the arrows are in the opposite direction, right? So if f of is an arrow from A to B in cat op, what I mean is f is really a functor from B to A, right? So it maps f op to some functor which is f upper star. So note that f is a functor from B to A implies f upper star should be a functor in this direction as we had, and map some functor, let's say f prime op, or let's say h maybe. I just want a different letter other than g. Okay, f1 let's say, and f2 op from A to B to f2 upper star, maps a natural transformation from f1 op to f2 op to some natural transformation here, which you can really figure out what this is. But the point is that this is a two functor, is a two-dimensional functor, something called a two functor, that is, roughly speaking, acts on uh, objects. Okay, I mean, I don't want to write this because this might only confuse you a bit more, but it's a two-dimensional functor. To spell out, it acts on objects, it acts on the one-dimensional arrows, and it also acts on the two-dimensional arrows, from one-dimensional arrow to another one-dimensional arrow, right? Now, an adjunction, so take A, take B, take F, take G, is gives you an adjunction. We have seen this previously. Gives an adjunction. We have seen this before that. If you take, I mean, A op, B op, if op is from A op to B op, G op is from B op to A op, but now F op is the right adjoint of that junction and G op is the left adjoint of that junction, and hence a pair of natural transformations satisfying the triangle identities, a pair of, or maybe a unit co-unit pair. This adjunction will give you a unit co-unit. This is an adjunction between of between functors, so and hence a unit co-unit pair satisfying the triangle identities. The interesting thing is that the triangle identity is entirely an identity about the two cells, right? It's equality of natural transformations, right? That's all that it is. And since this is a two functor, it preserves compositions, right? So it should map the identity to some identity of the image two cells, what I should say, really. So the point is that since bar comma c is a two-dimensional functor, is a two functor, so unit comma c comma the co-unit comma c yeah, is a pair of natural transformations. Pair of two cells are a pair of natural transformations. Satisfying the triangle identities. It is, and gives you, and hence gives an adjunction. There's something I'm a bit worried about. Just check whether the direction of the natural transformation is also preserved. I mean, if you take a natural transformation in cat op from f1 op to f2 op, does it actually give you a natural transformation from f1 start to f2 start? If it doesn't, then we also might need to reverse the two cells of cat. Okay, so we would have something called cat co-op. Yeah, and hence gives an adjunction of the, and hence gives an adjunction like this. So you have what did you have initially? Yeah, so let's say b comma c, a comma c. If was a functor from a to b, so this if upper star will be in this direction, g upper star will be in this direction, and you'll have an adjunction like this. You should have an adjunction like this. Okay. I would assume that the direction of the natural transformation is preserved. Yeah, it is. It is of course preserved. Yeah. Okay. Yeah. The point is, if you are interested in this two categorical perspective, have a look at this. Ignore if you are not. Okay. Because this might confuse you for the time being, since you are beginners in category theory. It's better to keep your priorities straight in the beginning. So ignore if not interested. I should mention this like a disclaimer. Okay. Okay, let's move on to the next problem. So suppose you are given a functor which is, I mean, this is again we are back in the one categorical world. Cat is the one category of categories and functors, and you take this op functor, which is from cat to cat, sending every category A to the category A op, the opposite category B to B op, and sends a functor F to the functor F op, which we have seen previously many times, right? So F op is a functor from A op to B op. So you take this op construction or take this op functor and use this to formulate the dual of GAFT. Okay, so let's first quickly recall what GAFT was. So the usual GAFT, let's put it this way. It says that suppose B is a small complete, that is has all small limits, locally small category. So suppose B is a small complete locally small category, and what else was needed? Yeah, a functor, I mean, yeah, this is, so a functor F, or rather maybe G, let's say, from B to A is or maybe has has a left adjoint if and only if G preserves limits and the solution set condition holds, right? Which essentially says that for each object A in A, if you look at the co-slice category A over G, then this category should have a weakly initial set, right? That is what the solution set condition essentially says. So what is this? This says that for each of, to be very explicit, for each object A in A, right, there should exist a set. This is very important. There should exist a set so yeah, bi comma A to gbi, right? Fi I in I of objects, let's say, or you can also put them as arrows, ignoring the first component of objects. Okay, let's I don't know what should we say. Let's forget the first component. Let's treat them as arrows, a set of arrows in A such that every arbitrary arrow A to GB F, let's say, factors, not necessarily uniquely, because this is just supposed to be a weak initial set of objects. So factors as so yeah, so what you have is A to GB, A to GBI, right? So from BI to B you should have an arrow, right? Yeah, because this is your weakly initial set. Yeah, so let's say this is G, I don't know, F prime, let's say. So A to GB you have F, this is Fi, right? For some arrow F prime from Bi to B, right? Yeah, that's all right. for some arrow bi to b, because a to gbi, a to gb. Yeah, that is what it means for it. Yeah, this is it. Yeah, so this is the general adjoint functor theorem. Let me quickly have a look. I just want to make sure that I didn't miss anything in this. um, or maybe okay. I don't want. Okay, I believe I didn't miss anything, but please do have go back and have a look. Yeah, for some arrow in B, I should say. Okay, so this is our usual GAFT. What we want to obtain, or rather formulate, is a dual version of this, and we want to use our op functor. So recall what does the op functor actually do? So the op functor maps a category A to its opposite category A op. So recall, what is the opposite category of a category? You take a category A. The opposite category A op is defined in this way. The objects of A op are the same as the objects of A. What you do is you flip the direction of the arrows, right? So in A op, an arrow from A to B is exactly an arrow in A from B to A, right? This is how the arrows of A op are defined, and this induces a composition from the original composition of A, and this is your opposite category A op, right? This is the opposite category construction. Now again, if you take a functor f from A to B, this actually induces a functor f op from A op to B op. We have seen what this functor is. What we want is, we want to formulate the dual of GAFT. So how exactly do we do that? So the idea would be to rather start with an okay, so let's write it and let's see. Okay, so we should write it first of all in the dual language. I mean, write the usual GAFT in the uh, I mean uh, by dualizing every statement in this entire GAFT, and then seeing what it happens for the original category. So I'll tell you what exactly I'm saying. So dualizing, or rather let's say GAFT. So usual GAFT for the functor G op from B op to A op. Let's write it properly. So what it says is, suppose that B op, we'll write the usual statement again. So suppose B op is a small complete locally small category. A functor G op from B op to A op has a left adjoint if and only if G op preserves limits, that is continuous, and the solution set condition holds. Which essentially says that for each object A in A op, there exists a set A to GBI, or rather G op of BI, I in I, if I op, this is a set of arrows in A op, right? A op, such that every arrow A to GB, I mean rather G of B, if op in A op factors as so A to G of B, A to G of BI, right? This is if op, this is if I op, and this is G op applied on some arrow if prime op. Okay. For some arrow if prime op from BI into B in B op. So this is the just the same statement but written for the functor G op now, from B op to A op. And now if you turn this, if you look at the original category, original categories B and A and the functor G, what does this statement translate to? So for every concept, every category theoretic concept will consider which I mean which pertains to the category B op or the category A op, we should come up with the dual concept which pertains to the category B or the category A, right? So dualization should be this now, that just translate this statement in the language of B. So suppose B op is a small complete, okay? So if B op is small complete, then B should be small co-complete. So suppose B is a small co-complete. Locally small is a set theoretic condition. So if B op is locally small, we know that B op of an object B comma B prime, this Hom set in B op in the direction from B to B prime is exactly defined to be the Hom set in B from B prime to B, right? Which means that if B is locally small, B op has to be locally small. This is just a set theoretic condition. So locally small will remain the same. Small co-complete, locally small category. A functor G op from B op to A op, so that should be replaced by a functor G from B to A. A functor G from B to A has a left adjoint. So think about this very carefully. We have covered this previously, that if A, B is an adjunction, F is a functor A to B, G is a functor B to A, and there is an adjunction with F being the left adjoint and G being the right adjoint, then if you look at the opposite categories, A op, B op, this is your functor F op, this is your functor G op. But now F op, there is an adjunction in which F op it becomes the right adjoint and G op becomes the left adjoint. So if G op is really if G op has a left adjoint, this would mean that G should have a right adjoint, right? That is, in other words, if F op is a left adjoint of G op, then F should be a right adjoint of G, right? So we should say So a functor G from B to A has a right adjoint if and only if G op preserves limits. So G op is a functor from B op to A op. G op is continuous, means that if you consider the functor G from B to A, this should, what should it do? Think about this. G op preserves limits, right? So G should preserve co-limits, right? That's the dual notion. In other words, if you start with a diagram in B op, look at the limit of this diagram, right? G op preserves this particular limit. Now a limit in B op is exactly a co-limit in B, right? In other words, if D is a diagram, or maybe if D is a diagram from I to B, right? D is a diagram in B of shape I, then D op is a diagram of shape I op in B op, and a limit of D is exactly a co-limit of D op, right? So in other words, G op preserves limits when translated in the usual for the usual functor G becomes G preserves co-limits. So if and only if G preserves, okay, so let's write the functor G. G is from B into A, preserves co-limits, that is co-continuous. And the solution set condition holds. Which is exactly this, that for each object A in A, there should exist a set G of Bi to A, Fi, I in I. Right? Note what happens. So Fi op is an arrow from A to G op of Bi in A op, which means that Fi is an arrow from Gbi to A in A, right? So there exists a set like this of arrows in A such that every arrow so A to G op B F op was the arrow in A op, so we should take an arrow G B to A F in A, GB to A F in A, factors as so what is this? GB, GBI, this is A. So GB to A we have F, GBI to A we have Fi. Yeah, I should also say for some, okay, yeah, I should say for some I in I, it's a weakly initial set of objects, right, in a category. So a weakly initial set in a category is a set of objects in the category such that for every object there is some object in our set together with a map from our from this chosen object from our set to that arbitrary object, right? So we should say for some I in I and for some arrow, yeah. So if prime op is an arrow Bi to B, so if prime should be an arrow B to Bi, F prime, this commutes, or rather Gf prime, for some I in I and some arrow f prime from B to Bi in B. I mean, sorry, in script B. And there you go. This is exactly the formulation. If you like to stay with the convention that left adjoint should be denoted by f and right adjoint should be denoted by g, you should just replace the letter g in this entire statement by the letter f. That's all. But the idea is simply this, that this is how we obtain a dualization, right? This is how we write a dual, I mean, form the dual statement of a certain statement or a certain notion, right? You just flip all the arrows in the statement, flip the order of composites, and we have seen previously that left adjoints are the dual notions of right adjoints. So whatever was holding for a left adjoint should get replaced by a right adjoint, right? Limits and co-limits are dual notions of each other, so limits should get replaced by co-limits. A functor preserving limits should get replaced by a functor preserving co-limits, right? That is, continuity gets replaced by co-continuity, and this is how you formulate the dual statement. So to be, I mean, if you prefer to keep, I mean, if you prefer to avoid the mentioning the solution set condition explicitly, then what we should have is, uh, instead of a weakly initial set for A, for the co-slice category A over G, what we should now have is a weakly terminal set for the slice category G over A, right? That is what, and that is exactly what we have here. Okay, so I'll just highlight the things that have been dualized or have a category theoretic dual. So small complete gets replaced by small co-complete. This functor g op b op to a op gets replaced by g b to a. The left adjoint gets replaced by a right adjoint. Preserves limits get replaced by preserves co-limits, and the solution set condition holds, which is, I mean, we entirely dualize this. We need to dualize this entire statement, which is exactly what we did here, right? So I'll maybe write the entire thing in a red box. So this is your dualization. Okay. So I'll just add a small note here. Recall from a previous exercise. Which is this, that if you have an adjunction G, so an adjunction with F being the left adjoint and G being the right adjoint induces an adjunction A op, B op, this is F op, this is G op, but now F op becomes the right adjoint. Okay. Yeah. Oops. So F being a left adjoint implies that F op is a right adjoint, and that is what we used here. Okay. Yeah, so that's the dual version of the GAFD, and let's quickly turn to our last problem for this evening. Okay, so let's read out the problem first. So for a set X, you consider the partially ordered set Px of subsets of X under inclusion. Okay, so take a set X, look at the set of all subsets of X. That's a partially ordered set under inclusion, so a category in particular. So let f from x to y be a function then observe that this induces a functor F inverse from Py to Px, which is exactly the inverse image functor. So what it does is, so the objects of Py are exactly, since this is a partially ordered set considered as a category, means that the objects of the category are exactly the elements of the partially ordered set. So in this case for Py, the objects of your category Py are exactly subsets of Y, and there is an arrow from an object, let's say Z, to an object Z prime if Z is contained in Z prime, right? So F inverse actually does give you a functor. Firstly, it gives you a map at the level of objects, sends any Z which is a subset of Y to F inverse Z which is a subset of X. And moreover, if Z is contained in Z prime, by which I mean that there is an arrow in Py from Z to Z prime, then F inverse Z is automatically contained in F inverse Z prime, by which I mean that there is an arrow from F inverse Z to F inverse Z prime. And this is a thin cat, I mean both the domain and codomain are thin categories, so it will automatically preserve identities and composition. So this is actually a functor. So what the question is, or the rather the problem is asking you to show is that show that F inverse has a left adjoint as well as a right adjoint. So I'll only do the left adjoint part and I'll leave the right adjoint part for you. So yeah, so let's start. So first of all, observe that F inverse Px, or instead of saying observe that, I should say the functor is given by sends Z to F inverse Z, sends Z prime to F inverse Z prime, right, and sends an inclusion to an inclusion, right? So this is actually a functor. So since the source category Py and the target category Px are thin categories because they are posets in particular, I mean because they are posets, they are thin categories, F inverse is a functor Py to Px. Okay. Now to guess a left adjoint for this functor, I mean we don't know if a left adjoint at all exists, but to guess one we could just, I mean since this category is simple, this functor is pretty simple, we could right away guess this. But why the problem was posed here is because I want you to use the adjoint functor theorem and first of all establish that indeed a left adjoint does exist. Okay. So maybe I'll put a note here that guessing a left adjoint and hence the left adjoint up to, which is unique up to a natural isomorphism. Guessing a left adjoint for F inverse is easy here, but we will first prove the existence of one. Okay. So how do we prove the existence of a left adjoint in this case for the functor F inverse? Using GFT, yeah. Using the Freud's adjoint functor theorem. So recall what are the conditions that you need to verify to show that F inverse has a left adjoint. First of all, Py should be small, complete and locally small. So the first condition, let's say, so let's verify the hypothesis of GFT. So what are they exactly? So first of all, since Py is a thin category, which means that if you take two objects, let's say z and z prime in py, then there is at most one arrow from z to z prime in py, which is indeed the case because py is a partially ordered set. Then so py is locally small. Right. What else? We need to verify that this py is actually small complete, right? It has all small limits. Okay. So uh, think about what small limits in py actually are, or what does a limit in py actually look like. So to study existence of limits, we know that it is enough to prove that the category has products and I mean arbitrary products and binary equalizers, right? Again, checking the existence of equalizers is trivial because the category is thin, so there is at most one arrow from one object to another object, right? So again, since py is thin, py has equalizers. I mean, so basically, if you take z and z prime, there is at most one arrow from z to z prime in py, right? So suppose you take two arrows f g from z to z prime, they are equal by definition. So the equalizer is exactly z together with the identity map from z to z. So nothing to verify about equalizers here. We just need to check for products. So okay, so let's write it here only. Let, or maybe here, let zi in I be a set of objects of py, right? That is, zi is a family of subsets of py. Question is, what is the categorical product, or what is the product of zi? So question is, what is the product of zi in I in py? So what is this product indeed? So think about it. What is the product of a family of objects? So it is an object in py, so it should be a subset of y together with maps to every zi, right? Which means that this product of zi's should be contained in each zi, right? Or rather zj if you prefer. And this should be the universal one among all, right? This object together with this family of arrows should be the universal one among all. So if you take an arbitrary object, let's say a, so if you take an arbitrary subset a of y together with arrows a to zj for every j, by which I mean that a is contained in zj, then there should exist a unique arrow from a to the product of zi's, such that the small triangles that you obtain commute, which actually commute because the category is thin. So what you essentially need to show is, or rather find, is a particular subset of y using all these zi's, which is contained in every zj, and moreover, if a is some subset of y which is contained in every zj, then a has to be contained in the product. So what is this product really? It's pretty easy to understand. Note that product zi in I is characterized by the universal property or maybe let's say is characterized or let's say let's write it like this, is the universal solution to the problem what is the problem? Problem is this, that a is a subset of y, a is contained in zj for all j in j, for all j in I, right? you need to find the universal solution to this problem. So product Zi is a universal solution, means that everything arbitrary, every arbitrary solution factors uniquely through this. Okay, uniqueness need not be checked because this is a thin category here, so it's automatic. So what do I mean by an arbitrary solution A factored into the product? This exactly means that A is contained in the product. That's all. Okay. So product Zi in I is that object of Py, if it exists at all. If it exists, is that object of Py, that is that subset of Y, such that product I in I Zi is contained in Y, and okay, so we already mentioned that this is contained in Zj for all j in I, and if A is a subset of Y, that is if A is an object in Py with A subset of Zj for all j in J, for all j in I, then A must be contained in the product Zi in I, right? So what is this really? What is this product Zi really? This is exactly the intersection. So product Zi in I is exactly equal to the intersection. Again, this is a poset, right? So skeletal category in particular, and hence any two isomorphic objects are equal. So product of Zi is isomorphic to the intersection, means that they have to be equal. So this is equal to intersection I in I Zi. Note that this is actually the product, because first of all the intersection is contained in every Zj, and if A is a subset of Y which is contained in every Zj, then A is also contained in their intersection, right? So products also exist. So products exist in the category what is your category? Products exist in the category Py. So Py has co-equalizers as well as arbitrary products. So Py is and by the way, it also has a terminal object. What is a terminal object, right? That is exactly Y, right? So in fact, you note that you can also understand this, because the terminal object is the limit of the unique functor from the empty category to your category, right? So here if you want to write the terminal object as a product, it should be a product of an empty family of objects, right? Which in this case should be the intersection of an empty family of subsets of Y, which vacuously is exactly Y, right? So it has all arbitrary products. So small products, I would say, small products, including terminal, including zero array, let's say, including zero array products, exist in the category Py. So Py is actually small complete. Okay, so what else do we need to verify? Yeah, so we need to verify whether the functor actually preserves limits or not. So need to verify whether F inverse preserves limits. So note that F inverse applied. So to prove that F inverse preserves limits, you just need to prove that F inverse preserves equalizers and arbitrary products. Checking for equalizers is is automatically true. You just need to verify for products. So note that F inverse of intersection, or let's write pi I in I Z I is F inverse of the intersection Z I in I, which is exactly the intersection over I in I F inverse of Z I. This is a fundamental property of inverse images, right, under a map. So F inverse preserves arbitrary products. In fact, note that F inverse of the terminal object, which is y, is exactly equal to x, all of x, which is the terminal object of px. So preserves arbitrary small products and preserves equalizers, which is obvious because the equalizer is trivial here, right? There is at most one arrow from one object to another object. So if you take two arrows f and g, they have to be equal. I mean, if you take two parallel arrows, they have to be equal, and the identity is exactly the equalizer. So F inverse, of course, preserves the identity because it's a functor, and so preserves equalizers. So F inverse preserves limits, that is continuous. Okay, so the last thing that one needs to verify is the solution set condition. Okay, so let's get back to our solution set condition. I believe this is it. So what we need to show is for each object A in A, that is for each object, object A in A here is Px. So for each subset U of X, let's say, we should be able to find a set of arrows in A such that every arrow factors as this. Now note that, I mean, okay, so let's get to this. Yeah. So we just need to verify the solution set condition. So take some object A in A, which is Px here. That is, take a subset A of Px. We should be able to find a family of arrows A to GBI. So G is our F inverse functor. So we should be able to find a family of inclusions. So A should be contained in F inverse of Bi, where Bi are subsets of Y, right? Such that if A is contained in F inverse of some B, then we should have a commutative diagram like this. Now, again, we are working in a thin category. So what this essentially says is that if f prime is an arrow Bi to B, then what this means is that some Bi should be contained in B. So what the solution set condition translates to is this. So we need a family, a set, I'll always mention a set of objects A contained in F inverse Bi, or let's write it properly. Objects Bi I in I with Bi a subset of Y, and A is contained in Bi for all I in I, because you need a map from, sorry, A is contained in F inverse Bi. You need a map from A to F inverse Bi, which essentially means that A is contained in F inverse Bi for all I in I. And what else? You take an arbitrary yeah, so if you take an arbitrary B, a subset of Y, such that A is contained in B, then you should have a commutative diagram like this for some arrow Bi to B, by which we mean that there should be some Bi. Yeah, I didn't write. yeah, for some I should write this for some I in I and some yeah, so there should be some bi which is contained in that b. Okay, and then this condition becomes automatic. Okay, because we are working in the thin category px. Okay, and if bi, I mean if b is a subset of y with a contained in f inverse b, then uh, then what? Then there exists some I in I with bi contained in b. So the question is, for the given a in px, what should a set of such objects bi be, such that bi is contained in y and a is contained in f inverse bi for all I in I, right? What should that be? What do you think? Keep in mind that the categories themselves are small here. Okay, so in particular py is a small category, it has a set of objects. Px is a small category, it has a set of objects. So what objects bi can we pick such that a is contained in f inverse bi for all I in I, and if b is contained, I mean, b is such that a is contained in f inverse b, then some bi should be contained in b itself. So what objects bi can we take for the given a? Sorry about the noise. Yeah. What objects bi can we take? Okay, so for the given a, how about we take bi to be equal to, let's say, f of a. I mean, what we are doing essentially is we are taking, in fact this actually gives you the explicit description of what the lift adjoint should be. So what we do is we take a singleton family in which bi is exactly f of a. Okay, so take I to be a singleton set. Okay, with b star is exactly equal to f of a. So note that a is a subset of f inverse of b star, which is f inverse of f of a. This is obvious, right? If you take a set a in x, a subset a in x of x, look at its image and then pull it back under f, then that f inverse of f a should contain a, right? So x is in a implies f of x is in f a, which implies that x is in f inverse f a, which implies that a is a subset of this. Now if b is a subset of y with a subset of f inverse b, what we need to show is this b star should be contained in f of a. Okay, then x in a implies f of x is in I mean x in a implies x is in f inverse b, which implies that f of x is in b, right? Which implies that f of a is a subset of b, right? This is for all x in a, so f of a is a subset of b. Okay. And now we are done. So solution set. So a solution set exists with B star. I mean, there is exactly one set. I mean, there is exactly one object. B star equal to f of a. Singleton family of objects. Okay. So conditions of GAFT verified. So f inverse from py into px has a left adjoint, and in fact we now know what the left adjoint is, but to explicitly guess what this is, so if let's say um, I don't know, let's say if lower star, let's say, is your functor from px into py, uh, is a left adjoint, of f inverse, then py of f star applied, f star is a left adjoint, so f star applied on some subset a of x, comma some subset b of y, this should be in bijection with px of f star, I mean a comma f inverse of b, which means, so there is a bijection from the left Homset to the right Homset. Both categories px and py are thin, so every Homset has at most one element. So what this bijection says is that there is an element in the left Homset if and only if there is an element in the right Homset. So which means that f star a, we don't know what f star a is, I mean we know, but just we want to guess this. So this is a subset of b if and only if a is a subset of f inverse b, which obviously implies that f star a has to be equal to f of a. So f of a is a subset of b if and only if a is a subset of f inverse b. Nothing nothing bigger than f of a can work, okay, and nothing smaller than f of a can also work. It has to be exactly f of a. Okay, so f star px to py, the left adjoint functor is given by sending an object a to f of a. And note that if a is a subset of a prime, then f of a is a subset of f a prime, etc., etc. I mean, once you guess what it does to the objects, knowing what it does to the arrows is straightforward actually. I mean, that uniquely gives you a functor up to certain conditions, yeah. So basically, I mean, it sometimes it turns out that to verify that something is a left adjoint to something, or rather some functor has a left adjoint, you can just show that there is a map at the level of objects which satisfies some naturality condition in a particular variable, and then that uniquely gives you a left adjoint functor. Okay, and besides these are thin categories, so nothing to worry about that. This is your left adjoint. So I would leave this the next part. So uh, finish the right adjoint part, or maybe show that your functor f inverse from py to px that we had has a right adjoint. So in other words, you basically have two adjunctions. Okay, so this is px, this is py. So from py to px we have this functor f inverse from Px to Py we constructed a left adjoint for this, which is f lower star, and you show that this functor also has a right adjoint. So show that there is a right adjoint and find that functor. Okay, I'll leave a question mark here with a in red color to indicate that this needs to be done. Okay. So there are actually two adjunctions here. One is an adjunction between f upper star and f inverse with f upper star. I mean, uh, f lower star uh, is the. I mean, and so one of the adjunctions is an adjunction between f lower star and f inverse, with f lower star being the left adjoint, and the other adjunction is between f inverse and some functor which you need to find, where f inverse is the left adjoint of the adjunction, and the other functor is therefore the right adjoint. Okay, that finishes stuff for today. We'll stop here, and do drop me an email if you have any questions, and please try to attend the sessions. Yeah, that's all. Thank you.